algebras and the cobar construction.
Thank you. So first of all, thank you to the organizers for the invitation, and also thank you, Paul, for having the energy of bringing people together and encouraging people to discuss ideas and talk. It's very encouraging. Okay, so I talk about Hopf group algebras. Okay, so here is the outline of the talk. All the time I will keep a field K fixed. Okay, so my coefficients will be in K in the field. And I will begin talking about topological quantum field theories, and then I move to Hopf group algebras, give the definition. I will, after the Hopf group algebras, give definitions of the cobar construction, and make a very brief historical overview of this construction. And then I will try to sketch results relating the two. Okay, and this is work in progress, right? So some of the results are not completely verified. Okay, so think of the category of n cobordisms. So the objects of this category are n minus one dimensional closed oriented manifolds, and the morphisms are equivalence classes of oriented cobordisms. So maybe I don't need to review what this is, but I will, just in case. So we make sure that we are talking about something we all understand, right? So all these guys are oriented, okay? So the cobordism is oriented, and the fixed manifolds, the closed manifolds, sigma 0 and sigma 1 are oriented, so I can talk about incoming and outcoming boundary components, right? So then I have sigma 0 here, and I have sigma 1 there, and let's say that I have two manifolds that are cobordisms, meaning that maybe I put some n here, meaning that I have a component of this manifold, of the boundary of this manifold, which is outgoing, okay? And then I have a diffeomorphism from sigma 1 to this component of the boundary. And then here, a diffeomorphism from sigma 0 to the component, to the boundary components that are incoming in the manifold. And same thing with n here. Okay, and then we say that these two cobordisms are equivalent if there is a diffeomorphism from n to m that makes this diagram commute. Okay, and sigma 0 and sigma 1 are fixed all the time. So that's the definition of equivalence class of oriented cobordism. And this thing turns out to be a category. So a category takes some work. So it's an exercise on differential topology and Morse theory to prove that this is indeed a category, okay? But it's not hard, but it's an exercise, a nice exercise. So yeah, we have a category, okay? It's n cob. And what is a topological quantum field theory? It's a functor from this category. Remember that I can make disjoint union of components of the boundary, and also the joint union of cobordisms too, okay? This picture is just an illustration, but this guy doesn't have to be connected, okay? So I can have this joint union of cobordisms too. Okay, so a TQFT, a topological quantum field theory, is a monoidal functor, so meaning that it takes the disjoint union to the tensor product in the category of vector spaces. Okay, so here just an illustration. So this cobordism M here is taking these two vector spaces because I have two components here, just to illustrate, in these two vector spaces here, and I have the tensor product because this is monoidal. And the same thing for the cobordism. So if I have two components of my cobordism, then I would have here the tensor product of linear transformation. Okay, so that's what a topological quantum field theory in general, I mean, not fully detailed, but that's the definition. Okay, now restrict to two-dimensional topological quantum field theory, then you have manifolds of dimension 2 is something that you have full control. And these guys here are the generators of this category, meaning that every cobordism of manifold of dimension 2 can be generated by the composition in the category of these guys. So these guys are generator, and I'm missing here the twist. So there's the cobordism that make the twist when you take the diffeomorphism that take two components and interchange them. And this is a diffeomorphism, so for every diffeomorphism you can construct a cobordism, and this guy is called the twist. Okay, it's here because it's not relevant for this Frobenius structure that I'm trying to describe. Okay, but you take this generator of this category in dimension 2, and it turns out that you can interpret, because you are using the topological field theory, so to this guy you have a product. To this guy, which is cobordism, in the output you have a circle, and in the input you have the empty set. It's a linear map that's a unit in A. And here you have one component in the input and two components in the output. Then you have a co-multiplication, a co-product, right? And then here you have a co-unit. So you have one circle in the input and the empty set in the output. And then you have a co-unit, is a map from A to K, right? It turns out that all this structure satisfies the condition for a Frobenius algebra. I will tell you what a Frobenius algebra is in a moment. And also you have this condition here, which is not hard to prove from topological, in topological way, but it gives you important information of the algebraic structure, okay? And then this theorem here is from, I think the pronounce is Gygraff. I'm sorry if I'm mistaken. Gygraff. Okay, so a Frobenius algebra is a finite dimension associative K algebra with a non-degenerate associative pair. So just a bilinear map that is non-degenerate, okay? And then what Gygraff proves is that there is an equivalence of categories between the category of two-dimensional topological quantum field theories and the category of Frobenius algebras. Actually, he works more generally in the context of conformal structures too, but this result is a particular case of what he was doing. Okay. Right. So that serves as a motivation for the study of coalgebras, right? So you have a co-multiplication. By the way, all those guys are associative, right? So this product here is associative, and the co-multiplication here is co-associative in a natural way. It's what you can imagine when you work with diagrams like this, and then you interpret the co-associative in terms of diagrams. It's the natural relation that you get. Okay. So now we take a group. It's a discrete group. It doesn't have to be finite, but it's a discrete group. What is a G coalgebra? So it's a family of vector spaces indexed by your group, and you have a graded co-associative coproduct. Okay, so for each component of your object, you have these maps delta GH, and they are co-associative in a natural way too. Okay, you have to write carefully in details, but it's just a graded coproduct that is co-associative, and you have a co-unit that works naturally also as a co-unit for this product. So essentially, when you have, like here, H is the identity, and then you plug in the co-units there, you get the identity in CG. Okay. Now, what is a Hopf G coalgebra? This was introduced by Turayev in the year 2000. So you take a G coalgebra as before, as in the previous slide, but now each HG is an algebra. Okay, it's a K algebra, but you know it's not graded like now. So HG itself is a algebra. It's not graded. But the coalgebra is graded, but not here. Okay, and then you have the antipode of the Hopf structure. What the antipode does is what this diagram is showing here. So here I'm simplifying the notation. Okay, so I just put E here, but this is HE because I don't want this diagram to be too heavy. So this HE, HG, HG minus 1, etc. So here is the coproduct. So you do the coproduct from E to G, G minus 1. Then you apply the antipode here, and then you multiply. Okay, and you get the same thing as applying the unit. The co-unit. So this is HG, HE again. So The co-unit, I think I forgot to say that. No, the co-unit is here, right? So the co-unit is only defined on age E. Then you apply the co-unit here, and then you apply the unit in the algebra. So these algebras are unital. Okay. And the co-product is an algebra morphism. Okay. You put all this together, you get a Hopf G coalgebra. If G is the trivial group, you have a usual Hopf algebra. You recover the notion of Hopf algebra. Okay, why he does that? Because of this. So this is of course, it's a rough description, okay? I'm not going into details, but we just seen that if you have Frobenius algebra, you can produce a two-dimensional topological quantum field theory. If you have a Hopf G algebra, you can produce a three-dimensional, meaning cobordisms are manifolds of dimension 3. Okay, so from this structure that we just defined, we can get three-dimensional topological quantum field theories. This is the result of 2AF. Sorry. Okay, now examples of this thing. You take a usual Hopf algebra, okay, and you take a family of associative algebras that are isomorphic to your original Hopf algebra. And these isomorphisms are indexed by G, of course, because it's a family of algebras and a family of isomorphisms. But this guy here is just an algebra, and this guy here is a Hopf algebra, and you can transport, because this is an isomorphism of algebras, okay? You can transport the coproduct here to this side, and you can transport the whole structure, and then in this family you have the structure of a Hopf G algebra, okay? I don't like the idea to call this example trivial, because age itself doesn't have to be trivial, and also you have a family of isomorphisms, which is something that can be non-trivial, but it's a kind of product. It's a kind of H times G. Okay. So if you take a compact Lie group, it doesn't have to be connected, and for each class in pi 0, you take the corresponding connected component in the group. Okay. And you take this family. So for each class in pi 0, you take the connected component, and you take the cohomology with coefficients in K, right? And this is a Hopf pi 0 pi 0 gamma coalgebra, okay? But this is of that type, because all of these algebras are isomorphic. You take conjugation by an element that is in the connected component, and you do the conjugation, you have an isomorphism with the component in the identity. So it's an Hopf coalgebra of this type. And there comes the question, okay? How can I construct a example that's not of this type? Using algebraic topology, okay? Maybe you can construct examples by other techniques, but I want to use algebraic topology to construct an example that is not of this type. And of course, we want to use the simplest possible technique, the simplest possible construction. Okay, it turns out that I tried many ways and I fail all the time. Or I don't get the Hopf G coalgebra, or I get one that's H times G, which I don't want. Okay, so the co-bar construction is one possible construction that you could use to produce examples that are not of that type, that are not of H to the G. Okay. So Adams in 1956, proved this quasi-isomorphism here, but he requested the topological space to be simply connected plus another conditions, so it's not any space. So it's a simplicial, it's a cell complex with the skeleton in dimension 1 must be trivial, and it has to be simply connected. Okay, and then you have this quasi-isomorphism. What is a quasi-isomorphism? So all of these guys here are differential graded algebras. So this is the co-bar construction. I will explain it in a moment. And this is just singular chains in the loop space of X. Okay, so you have a differential graded algebra here, and the co-bar construction gives you a differential graded algebra here. And these guys are quasi-isomorphic, meaning that you have a chain map between them, and it induces an isomorphism in homology. But what Zainalian and Rivera did in 2019 is they prove the Adams isomorphism without the simply connected condition. To do that, they used the rectification functor from Jacob-Lurie, and they used Quillen adjunction. Okay, they use model category, the Quillen theory of model categories. Okay. And then, but now they remove the condition of X to be simply connected, so this guy now is alive. Okay, and then when you take this quasi-isomorphism and you do H0 here, you have this isomorphism. Now, you see in a moment that inside this construction there is some suspension. So you desuspend the elements of your complex. So when you apply H0, you have something that's not trivial because of this suspension. Okay. So this is in the paper of Zanelli and Rivera. So what this story tells us is that, yes, you can use the Kobar construction to produce some examples of Hopf algebras, but these are standard Hopf algebras. Okay, so before I give the definition of the Kobar construction, let me just make a brief historical overview. So Adams introduced it in 1956, and he was interested in compute the homology of loop spaces, okay, and then there are some conditions on X. So in 1963, Jim Stashev studied the Eilenberg-Moore spectral sequence that arise in the bar construction for infinite algebras. So he introduced infinite algebras. He showed that it's possible to make the bar construction for infinite algebras. And then there is a spectral sequence, there is a filtration in the bar construction. You have a spectral sequence. This spectral sequence is the Eilenberg-Moore spectral sequence. The differential in the spectral sequence is given by a generalization of massive product. And then in his book of, well, I don't remember, I think it's 71, he used this bar and Kobar adjunction. So essentially, the Kobar construction is the dual of the bar construction. There is an adjunction between this functor, and then he gives the outline of another proof of the Adams isomorphism. This is in the beginning of the 70s. Okay? Then in 1981, Bowis proved the existence of a DG bialgebra structure on the Kobar construction. Okay, but again, X has to be simply connected. And then the work of Bowis led Getzler and Jones to define B-infinite algebras, and then this began being studied. Part of these B-infinite algebras are the A-infinite algebras of Stashev. So there are many things to talk here, but I don't have time. And then there's the result of Zanelli and Rivera in 2019 that we already spoke about. Okay, so what's the bar construction? I will try to give a simplified version. So there's some technical details that I'm omitting, but we can talk about it during the coffee break, maybe. So you take a differential Z-graded coalgebra, and this Z-grading here doesn't have to be confused with our grading by a group. So it's something different. So here it's graded by the integers like a complex. Okay, but then graded by the group is another thing. And then you request that this guy is to be 0 for n is smaller than 0, and then you make the reduced, because you are going to desuspend this guy, so you need to reduce before the suspension. And for I bigger than 0, you don't have to reduce, you keep the same element. Okay, and then you take the coproduct in this coalgebra, and then you kill the components of the coproduct that lives in these 0 elements here. So this is the reduced coproduct. And then also you can restrict the differential, because remember, this is a differential coalgebra. So there's a differential operator, and the delta here is a chain map. Okay, so these guys are chain complexes, and delta is a chain map. Okay, then you just do the tensor algebra, so you just take all the tensor products. It's the free associative algebra generated by these vector spaces. And this -1 here means that you declare everybody have degree 1 less. Okay, you desuspend the degree of all the elements there. Okay, and then you define this D. D is a differential operator. How you do that? You take the differential of C, you take the coproduct, and then you extend this as a derivation in this algebra here. Okay? But because you have a D-suspension, so it's not quite this, okay? You have to adapt the degrees of this guy. So this is not totally accurate, okay? You take this guy here, but you adapt the degrees, and then you expand, because the algebra is free, okay? It's the free algebra generated by this guy, D-suspended. So you can extend this linear map as a derivation, okay? It turns out that D squared is 0, okay? Because this guy is co-associative, this guy already, D squared is 0, and this delta here is a chain map with respect to D, so D squared is 0 here. So you have a, should be here somewhere, so you have a derivation differential, okay? A differential that is a derivation. So that's your Kobar construction, okay? You take the suspension, you take the reduced coalgebra, you take the tensor algebra generated by this guy with this differential that you built here, and the product, this is the product, and the product is just the product in the tensor algebra. You just concatenate. You take an expression given by tensor, and you put them together. So, okay? Yeah, that's the Kobar construction, and that's the construction that is in all these stories here that we were talking before. So this is the Adams isomorphism. Okay? That guy here is the one that we just defined. Okay, now let's move to a different approach. So this is the work of Canepel and De Lombard from 2004. They defined the Turayev category. Okay, when C is a monoidal category, is a very simple definition. So the objects in TC are just families. Let's say X, A, and S is just a set, and XA is an element in your category C. Actually, they did this for the category of vector spaces, but you can do for any symmetric monoidal category. It doesn't have to be symmetric, sorry, for any monoidal category. Okay. Okay, so S is just a set, and then the morphism. So you have like X, let's call this X. We know subindex is the whole family. Okay, and then here Y is another family. And then you have a set over Y, let's say T, maybe. And you have a set here S. And you want to define a morphism from this object to this. Okay, what you do, you take a map on the other way, so it's a sort of pullback, okay? And so this map is F, and for each, let's say B, maybe in T, you have a map from X, F of B to Y of B. So you can maybe have some intuition thinking that this guy is given by differential forms, or of maybe the dual of the tangent space over this guy, and then you take the pullback. So you have a map. So you can interpret this set as being a base of a fiber bundle, okay? So this is just interpretation, and then this guy is sort of pullback. Okay, you're going the other way around here. That's the definition that Canepel and De Lombard gave in 2004. Okay, and they call this category the Turayev category. And they proved this result that's there. Okay, so this category is a symmetric monoidal category, this one here. And because this is a symmetric monoidal category, you can give the definition of a Hopf algebra in any symmetric monoidal category. You just mimic the same definition that you have of a Hopf algebra. You just transport the definition to this category, and you have the notion of a Hopf algebra in any symmetric monoidal category. Okay, so and if you take a Hopf algebra in this category, you have the definition that you just gave. Okay, it's a definition of a Hopf G coalgebra. For example, if you do a Hopf algebra in the category of sets, what you get is just a group. Okay? So group is a Hopf algebra in the category of sets, just as an example. Okay. And now, from now on, this is a work in progress. Is the idea of how to produce example of Hopf algebra that's not h to the g. So you take an object in the Tureyev category of the topological spaces, okay, and you define a loop space of this object. It's relatively simple. You just take loop spaces on any space here. But remember that you have, you need a base point, right, to take loop space. So some comments here. What you're doing, you're taking a comonoid or a coalgebra. It's just a matter of language, okay? When I say coalgebra or comonoid, it's because I am in a symmetric category, so I can use these words. They mean the same thing. But remember that these morphisms here go in the other way around, right? So if this guy is a comonoid, I have a coproduct. But in the base, because of this rule, I have a product in M here. So if the whole thing is a comonoid, then M is a monoid in the category of sets, because this S here is just a set. So when I do this, I have a monoid. M is a monoid, and I have the coproduct, which is something like this: A, B, X, A, B. This is the product in the monoid. X, A, X, B. This is the product in your symmetric category. In our case, it's top, so here is the Cartesian product of topological spaces. So this is the first comment. Because I'm taking a comonoid, then M is a monoid. The second comment is so if I'm going to take loops, I need the base point. Okay, and I need the base point in each element. So this comonoid, this coalgebra has to be co-augmented. Okay, I need a morphism from the identity element, because this is a monoidal category. There is this unit element in this category, so I need a morphism. So A. Okay, and what this morphism gives us is precisely one base point in each XA. So then you can apply the loops. Okay. So you apply loops on each of them. And then you can apply also the singular chains on each XM. Okay, and in that case, yeah, we still have a coalgebra, but then in a different category. Okay, it's a coalgebra in the Tureyev category of chain complexes. Okay, now we have a differential. Okay, this is just the idea of a project. Okay, some details are not completely done, and then you apply the cobar construction on each of these coalgebras here, because this guy is a differential coalgebra, so I can apply the cobar construction and apply it on each one of them. Okay, and then there is this question of the group completion, which I mentioned in a moment. Before we move, let me just mention this. So, what is a Cartesian category? Talking roughly, it means that you have a monoidal category that looks like sets. Okay, this is not, of course, it's not a definition, but it is the idea. So you have a monoidal category, you have a product, a tensor product of objects, but the behavior of this tensor product is just as the behavior of the Cartesian product in sets. Okay, and then you call this category Cartesian. So in that case, any Hopf algebra that you take here, remember the theorem of Canepel and de Lombard. So if you take a Hopf algebra here, you get a Hopf G coalgebra. Okay, but if you do this with a category that there is Cartesian, you end up with the thing that we don't want. Okay, we don't. This guy is nice, but it's not what you want. Okay, so we need to avoid Cartesian categories. Okay, so this is a theorem that I believe I can prove. So there is a quasi-isomorphism of algebras because when I apply the Kobar construction to a coalgebra or a comonoid in the Turaev category, I get an algebra in the Turaev category. So this is a quasi-isomorphism of algebras in this Turaev category here on chain complexes. Okay, and then we need to apply a suitable form of group completion to get this result on homology in degree 0, which is, I hope, it is an extension of the result of Zainalian and Rivera. Okay. Well, there is this point of the group completion here that we could discuss, but I just mentioned why we need to do this. Okay. So if I begin with a group here, then we end up with this situation. Okay, so if this M here is already a group, then we will not get what we want. So we will fall in this situation. So I cannot begin with a group. Okay, I need to begin with a monoid. That's not a group. But then I move to another category, which is an algebraic category of vector spaces. It's no longer a Cartesian category. Okay, then I can, after I move to another category, which is not Cartesian, then I can perform the group completion to get a Hopf group coalgebra, okay, because what we are looking for is a Hopf group coalgebra, okay? And then I believe that these quasi-isomorphisms here restrict to this one. But there are some issues here on how you define this functor here, because this is a functor, okay? I begin with a monoid in the Turaev category of topological spaces, and I apply two functors here. So I applied pi1, and then I apply k, okay? But these must be coalgebras over the group completion of M. So there's some definition here that's necessary. I'm not giving this definition now, but if someone is interested, we can discuss this in the after the talk. Okay, so here are the references. If you are interested in topological quantum field theory, I suggest you to read Joachim Koch. So this is the introduction, but it's just for those who never seen this and are interested. So this is the book, okay? If you want to read more about Hopf G coalgebras, so this again is a book. So you look for Vladimir Turaev, and he has this book. And if you want to read more about the Kobar construction, the book is this one, Marco, Schneider, and Stashev. Okay. So yeah, I would have more to say about this group completion, but I prefer to stop here. And if someone is interested, we just come and discuss. Okay, so there are lots of details to be filled in this part. Okay, why do we really need the group completion here? Okay, thank you, Paul.
Okay, thank you very much for your conference. Are there any questions or comments? Okay.
I'm curious about why you didn't stay at the level of a monoid. Is it only because Turaev wanted to?
It's only because I want the example of the definition of Turaev, which is a Hopf group coalgebra. So,
right.
So to have the Hopf structure, I need the group. Just because of that.
What is it? You needed
the because you know you are in the Turaev category, okay? So in the top you have objects in the your monoidal category. Right? The word disappeared. And in the base you have sets. But a Hopf algebra is in sets is a group. So if you have a Hopf algebra in the Turaev category in the base, you must have a group.
So it's the old business that a bialgebra is not a Hopf algebra because you don't have the inverse.
Exactly. And then when you are in a Cartesian category, you have only one choice for the coproduct, which is the diagonal. So
good.
Yeah.
More questions? I just have I mean, I'm not a specialist. Okay, so I have a question, perhaps naive, but what would be the motivation to I mean, you want a family that is not HG. What would be the motivation for this?
Well, no, this is began with curiosity, actually. But then I think, and then I tried very hard to produce an example, and then I fail all the time. But then I came up with this idea of taking a commanoid in the 2IF category. And of course, it's not any commanoid that you're going to give you something that is not HG. So there should be some condition on this guy. And I want to learn what this condition is. But then after that, you can start thinking about what kind of topological point of view theory you have when you have some half-algebra of this kind. But this is another step, right?
I mean, I think that my question was more on that direction. I mean,
But actually, it
what
began
kind
with
of
curiosity,
physical
but-
models would you get
Yeah.
with something that is
What is
not
the condition
an
of the
HG?
monoid to have something that's not HG? Because of course, there's some monoids that you're going to end up with something that's, let's say, trivial. Okay, there should be some condition on the commanoid such that the result is not trivial. And what the condition is, I don't know.
Okay.
And what kind of topological future you get
sure.
for this kind, but this is a second step.
Okay, great. Thank you very much.
Okay.
So let's thank the speaker again.
Thank you.
Break of about 20 minutes, is that right? And well, we come back on 3:30 or 3:40 perhaps.